right. So I'll be presenting. I'm a PhD student in Leuven, and my main topic is actually knowledge representation and reasoning. But for this case, we're trying to look into combining our mainly theoretical knowledge with the useful things in the communities here, such as DMN. Now, DMN, DMN is a way to model business decisions, and here you have a decision requirement diagram, which displays the dependencies for making decisions. So, for example, the eligibility for insurance depends on the client score and the fact whether the client is a long-term client. You can do it all the way down. For example, the potential theft rating depends on whether it's a high theft probability auto, the price, whether it's a convertible. Now, this is just a dependency. The actual decisions can be modeled using, for example, decision tables. So here we have a decision table, which says, well, an at-risk model has always a high potential theft rating. A convertible, also. If it's an expensive car, also. If it's neither of the previous ones, if it's a moderately priced car, you have a moderate potential theft rating. A low-priced car has a low potential theft rating. So this is a notation for clear business decisions, and business people can use this. And there are a couple of systems which can actually do useful stuff based on DMN models. And most of those can use these models to calculate from the inputs the output. And it's useful in many ways, and business rule systems are very good in such stuff. But actually, maybe we can do more with this. Because in such a table there's information. And information doesn't do anything. We do things with information. And we can do much more with this information than just executing it from left to right. DMN doesn't say anything about execution, so your systems can do much more with it. And this is what we call the knowledge-based paradigm, saying you have a bit of knowledge and we can do stuff with it. So we propose to use a knowledge-based system as a multi-directional execution system for DMN. Not just executing left to right, we can do all kinds of reasoning tasks based on this DMN specification. And the concrete knowledge-based system we're developing ourselves in Leuven, is the IDP system. So it's a knowledge-based system based on first-order logic plus some extensions. The most notable one is support for inductive definitions. In short, avodat. The dot stands for the extensions we support. Now, how do we use such a knowledge-based system? Well, we first specify knowledge, saying what are you talking about, and what do you know about the things you're talking about. So what are you talking about? We do such things in a vocabulary, saying I'm talking about prices, which can be low, medium, high, about theft ratings, low, medium, high, and then some propositions like convertible, high theft probability auto, and a car price and potential theft rating. So these are the things I'm going to be talking about. Then, what do you know about it? Well, we know the DMN table, the decision table, DMN specification. Unfortunately, we didn't yet arrive at an automatic translation from these tables to to our systems. But we have good intuitions about them, and we have done some use cases where we have shown that it's easy to translate in at least some cases. So here is the IDP FODOT specification of the same knowledge. We say the potential theft rating is high if it's a high probability auto, if it's or if it's a convertible, or the car price is over 45k. It's moderate if the car price is moderate. So you see there's a very large correspondence between the rules here and the rows in the decision table. This is not automated, but there's a very strong correspondence, and the automation is a work in progress. So we know this definition. So now we have specified our knowledge in the knowledge base system, but we still can't do anything with it. The last step is being useful. So then the question we ask is, what is the required reasoning task on this knowledge? Well, what could we do with the knowledge we have here? Well, the most obvious thing is what the business rule systems would do, deriving the conclusion from the premises. But maybe we could do what-if scenarios. What if I change some input? What if I change some rule in the table? We can handle incomplete data. What if I don't really know how much the car costs? Can you already say me something about the probability of theft? And we combine all these in what we call determining consequences. Consequences of the information we already know. Given this set of information and this theory, can derive me everything you can derive. But we also have other reasoning tasks, such as expanding a partial solution to a full solution. Saying, well, I want a solution where I have a car which was very cheap, but it's still a high probability theft car. How could that happen? This reasoning task could give me a scenario where that happens. Or I can do optimization. Like, in what situation would I have the least probability to have my car stolen? Or verification. Give this information to a theorem solver, theorem prover, to prove certain properties about the model. So we can do lots of different reasoning tasks based on the same piece of information. So we developed a web-based tool, which is publicly available. So here I just put in the theory, the exact same definition as I showed you earlier, and I can really interactively play with it. So if I check, okay, I don't have a convertible, it was a medium-priced car, then I already can see, well, the potential theft rating is certainly not low. I cannot derive whether it's high or moderate, but I can see it's not low. Based on the last piece of information, I have the complete information, like you would have known with traditional systems. So you can see I can interactively play with it. Or just give me a random situation where the potential theft rating is high. I can do this by selecting, I know it's high, and I ask expand to a model. So you see, I used the decision table in the opposite direction. Another thing is, I like to stress, is the maintainability of such a thing. What if now self-driving cars arrive? Then probably self-driving cars are a big target for theft. So you change the DMN specification. How much should change in the IDP thing? Well, very little. So here is the thing I showed you earlier. I just say, I talk about something more. I talk about the proposition self-driving. And I say, well, the potential theft rating is also high if it's a self-driving car. Our system automatically can work with the new property, it's there, and if I select something, it automatically reacts to it. So we have a very easily extendable system which is completely dynamic. But up till now we just used like a decision table which is always rules, but we can even do more stuff. I have an example here from a DM challenge from last year, where the challenge was to make a good burger. You have some items which have properties like the amount of sodium, fat, calories, and its cost, and these together make a burger. You have to have all the items, but there are also some health limitations on burgers. It can't contain too much sodium, fat, or calories, and for flavor reasons, servings of ketchup should be the same as serving of lettuce, pickles, tomatoes, and at most five of those items should be in each burger. Now you can ask questions like, what would be the cheapest burger? What would be the most expensive burger? You can make a DMN model for this, a decision model, which would contain information like this: the amount of sodium in total is the amount of sodium in in one patty times the amount of patties you have. Then you say all burgers are the amount. A burger is an amount of items for each kind of item. The count is between 1 and 5, and the allowed burgers are the burgers who are healthy enough. Well, now if I just put this in RDP, you can see it's a very concise representation also, and things like equalities just work. And we can do nice stuff like, what if I have a burger with 5 buns? Oh, then I can't choose 3, 4, or 5 slices of cheese. So you see, this is a question which is not that obvious to solve, but in a knowledge-based system, it's very easy. And we can also do the optimization. Give me the burger with a minimal price. Well, obviously the burger with one of everything. But with the maximal price would be less obvious. It would be this burger. I wouldn't want to eat it. So, I didn't say much about execution. Well, I told you, you specify knowledge, something happens inside our system, and then we get there. Well, what do we actually do? We don't have one unique execution inference. We use techniques from answer set programming, constraint programming, SMTs, tier improvers, and we try to combine them or even use those other systems when appropriate to have a good execution of of the required reasoning task. So you see, we're not afraid to use other systems because they can do those reasoning tasks very good. Don't reinvent the wheel. Make new technologies if you can reuse good existing technologies. So we made another more elaborate demo which just shows IDP can handle more than just the toy examples I showed you earlier. So we can reason in all directions. So if you ever think, well, now I should reason backwards from this decision table, you can just say you're combining DMN and the knowledge-based paradigm for flexible decision enactment. Thank you very much.
second is more, if you use uncensored programming or this or that, in which sense is your approach based on first-order logic?
Well, we have one language with a model-based semantics. And the model semantics dictate what you mean when you write something. Depending on the reasoning task you ask from the system, it decides to do different things. For example, determining consequences could be very expensive, so we actually have 2 or 3 ways in our system to determine consequences. One is symbolic, which just symbolic reasoning on the theory. One fully grounds it to SAT and does full optimal propagation in SAT.
The question was, how do you choose among the possibilities?
You have to specify what reasoning task and what
Who?
the user. Sorry. The one asking the question should say, I want to use this reasoning task with this kind of implementation, but everything comes out of the box. But you have to choose, like, okay, this is a big theory, I won't get there with this heavy inference. But
another question. So to understand the translation process, you translate from DMN into first-order logic, and then from first-order logic into the languages of these reasons?
yeah, but most of the things, the main thing, like the model generation thing, isn't we have implemented ourselves, but we use techniques from ASP inside our own reasoning system. Tier improvers, for tier improving, we use external one, but we translated DMN to FO dot, including the indicative definitions, which are quite important for some of these cases.
And it's using the XML series.
We did it manually for now. We didn't have an automatic thing, but we have strong indications that it would be feasible to do automatically. But it's work in progress.
The application of using the reverse direction of the rules reminds me of the direction rules in C.
I don't know it. Sorry.
Well, okay. I guess we'll have to see, because that project, that definition of using the reverse direction of the rules is probably similar to what you are using, but it's mathematical.
I don't know it very well, but I would suppose there are some systems which can reason backwards, but can't combine reasoning forwards and backwards at the same time. And that's one of the unique things about our system, is that we don't have a fixed direction, and we can combine all the directions at the same time. If we have some inferencing we need to do forwards, and at the same time something else backwards, we can do it. I can't comment on how the system did it, how your system does it, but I would suspect it's only